Hi, my name is Joe. I've been thinking about the twin prime conjecture for about a year and a half now, I think, and I think I found a way to prove it true, so I'd like to talk about that now. The twin prime conjecture, it states that there are an infinite number of twin primes, and a twin prime is a pairing of prime numbers that are two apart. So, for example, 5 and 7, uh, and 11 and 13. Those are two examples of twin primes. So in order to get to the main core argument, I have to build up some context. So we'll start here in this divisibility chart I made. Let me zoom in. So what you're looking at is numerators and denominators, starting at 1, going to 13, but really this goes on to infinity. I just don't have time to write that. What it really shows is if a number is divisible by another. So to read this chart, it would look like this. We'll start at number 8 here, and go across. We see a 0 here, which means that 8 is divisible by 1. We go across, see another 0, 8 is divisible by 2. Okay, what does the 1 mean then? It means that 8 is 1 away from being divisible by 3, right? 8 plus 1 is 9, and 9 is divisible by 3. Keep going, we see a 0, 8 is divisible by 4, and we see a 2. 8 is 2 away from being divisible by 5. 8 plus 2 is 10. You get the idea. And that's how you would read it. That's how you would read the chart going from left to right. Let me undo some of these markings here. So I've only done 13 numbers, as you can see, but you can already notice a couple of patterns emerging, and let's talk about those now. So one thing is there is a line of zeros going down on the first column, which makes sense, right? Every number is going to be divisible by 1. Similarly, every number is going to be divisible by itself, and so you see another line of zeros. This time it goes down diagonally. So a prime number, it can be divisible by 1 and itself. That's sort of the definition, so we can really ignore those two lines and look what is in between. So I'll draw that now. If I can, a triangle in between the diagonal and the vertical line of zeros. You might be asking, what about the right hand part? All these numbers that come to the right hand side of the line of zeros? Well, those are never going to be useful because a number is never going to be divisible by something greater than itself. And what we really care about inside of this triangle is the appearance of zeros, right? Because that would mean that it is divisible by something other than 1 and itself, which would make it a not prime number. For example, 4. We see a 0 in between the triangle, so we know it's not prime. However, 5 and 7, we see there aren't any zeros, which indicates it is prime. There's also another thing I want to note. There's a jigsaw piece sort of down the middle of this triangle, sort of. I'll draw it now. It's right here. And anything to the right of this jigsaw piece is also going to be non-zero, and that is because a number is not going to be divisible by anything between itself and half of itself. For example, 10, the biggest factor of 10 is 5. Anything more than half of 10, anything between 5 and 10, is not going to be a factor of 10, if that makes sense. So we can also sort of ignore these numbers on the right hand side of the jigsaw piece. Also, the columns. Say you have this column 2 and this column 4. Well, every number divisible by 4 is also going to be divisible by 2, right? And so what you get is a redundancy of zeros here, like on the 8 column. This 0 really isn't useful on the 4. So what we can do is make a new chart where we only look at the triangle part and only look at the left-hand side of the jigsaw piece. And we take out all of the non-prime columns. And what we get is a divisibility chart version 2. And what this essentially gives us is a string of numbers, which I call a divisibility string. And within this string, if there are any zeros, the number is not prime. So, what are we looking at here? Well, a twin prime, primes that are 2 apart, do we notice anything different about them? It seems that they only start with a 1 and a 1. Does that make sense? Yes, because the second column can only be a 1 or a 0. And zeros are no good, right? It means the number itself is not prime. So the first column must be a 1. And what about the third column? Or, excuse me, the second column, the 3. It can be a 2, a 1, or a 0. Zeros are no good. It means that the number itself is not prime. And a 2 is also no good, because it means the number 2 away is not prime. So the only way you can start a twin prime is if the divisibility string starts with a 1 and a 1. And what we care about after that is if any of the columns show a 0 or a 2, for the same reasons I just explained. A 0 would mean it's not prime, and a 2 would mean the number 2 away is not prime. So, how often do these appear? Well, column values, they constantly loop, right? 1, 1, 0, 0, 1, 2, 0, 1, 1, 0, 0, 2, back to 1, 1, and then we continue the loop. So we hit 1, 1 exactly every 6 numbers. And in other words, every 6 numbers we gain a twin prime candidate. And as I sort of hinted at earlier, candidates are disqualified if any of the remaining digits are a 0 or a 2. And I sort of explained that already. Okay. Now there's an interesting, I guess, phenomenon with how these numbers loop. And it's because every candidate is always 1 away from being divisible by 6, right? Because you're starting at 5, which is 1 away from 6, but you're adding 6 to get to the next candidate, which is 11, and now you're 1 away from being divisible by 6 again. So what happens when you're checking every 6 numbers? Well, look, for this third column, you can have a 4, 3, 2, 1, or 0. If you start at 4, what happens in 6 jumps? You go to 3, 2, 1, 0, 4, then back to 3, 3, 2, 1, 0, 4, 3 to 2. So you hit every single number in the loop exactly once with no duplicates. And then you start again at 4. What about for the 7 column? Well, you can have a 6, 5, 4, 3, 2, 1, 0, and you do 6 jumps at a time. 6 to 0, 0 to 1, 1 to 2. Again, you hit every single number exactly once with no duplicates. And this happens every single time because all these columns are prime numbers that are 1 away from being divisible by 6. All these numbers that's greater than 3 onwards, which is what we care about. So these divisibility strings can be disqualified by more than one violating column. For example, you can have a number that's divisible by 5 and 7, so you would get 2 zeros. But for the sake of the argument, we're going to assume the worst. So we're going to calculate the worst possible number of disqualifications additively. And how we would do this is as follows. So we'll start with 600 as in. We're going to go down the number line until we hit 1200. So we gained 100 new twin prime candidates, because 600 divided by 6 is 100. And we ended at 1200, so we only need to check the string up to the largest prime that is less than 1200 divided by 2. And we already know that the first two digits of the string are 1 and 1, so we can start looking at the third. And we know earlier, looking at how the numbers loop, that there is going to be exactly 2 out of every 5 candidates that have a 0 or a 2 as their third digit, which would disqualify them. So we're going to take the total number of candidates we have, divide by 5, and multiply by 2, and we get 40. 40 candidates are disqualified by the third digit alone. And then we're going to calculate this additively, right? So the next digit is the 7 column. And the 7 column, we know that every 2 is also going to have a 0 or a 2 as their fourth digit. So we're going to do 100 divided by 7, multiply by 2, and get 28. But wait, 100 does not divide into 7 evenly. You get 2 left over. So we're going to assume the worst, right? We're going to add that to 28 and get 30. And we'll have 30 of those original 100 candidates get disqualified only by the fourth digit. And what we're going to do is keep doing this until we reach the prime that is less than half of n. And we're going to add these all together, right? So 40 plus 30 equals 70, and then we'll keep adding it. And we'll get a total number which will be the worst possible case of disqualifications. So what I did basically was create a program to go through a bunch of numbers and calculate the amount of candidates we're getting and calculate the worst possible disqualifications. And what I got was this chart here. So TPCs are twin prime candidates and the WBDQs are the worst possible disqualifications. So you can see when n equals 60, we get 10 new candidates and 34 worst possible disqualifications. And when n equals 600, of course, we get 100 candidates and we get 387 worst possible. So you'll notice that throughout this entire graph, the worst possible is always greater than the candidates, which isn't good for my argument, right? Well, how are they growing is the question now. So every time we bump up the exponent by 1, we get 10 times as many candidates. So in this graph below, you can see this purple line at 10. That's indicating the multiplier of twin prime candidates. And these other dots, these little points, are indicating the growth of the worst possible disqualifications. So we start here at 11.3 times, and we go down to 10.7, 10.6, all the way down to 10.4. And it seems to be a logarithmic function. It's going down. And if there is a point where this pattern continues and dips down below the purple line, what would that mean? That would mean that the total number of disqualifications is growing slower than the candidates. So at that point onward, TPCs will be growing faster than disqualifications. And we know this is true because we know primes become less dense as we move down the number line. So this multiplier for disqualifications will go strictly down. And at that point, the growth will change, like I said. And at a much, much, much larger number, there will be a point where there are actually more candidates than there are disqualifications. Worst case scenario. So at that much larger number, we can call it capital N, we would be guaranteed a twin prime between n and 2n. And this is because between n and 2n, there is a certain number of candidates that is more than the worst possible disqualifications. So after all the disqualifications happen, there are candidates left over, and all of those candidates have to be twin primes. Okay, so what this basically comes down to is if we can ever prove that the multiplier of worst possible disqualifications dips below 10x, then I think the twin prime conjecture has to be true. So I was limited to 60 million numbers because the program I wrote wasn't really optimized, and the PC I ran it on wasn't very fast. But if we can run a similar program on a faster computer and show that this graph does dip below 10x, I think that proves the twin prime conjecture. But please let me know your thoughts. Thank you.